Hello, welcome to our video tutorial on flash storage. We will be discussing flash storage definition, history and background, importance, purpose, and its functionalities. We will also be giving you some insights about its images and its advantages and disadvantages. We will also be giving some technologies or the current technologies associated with flash storage. So before we proceed with samples and its advantages and disadvantages, let's first define what is flash storage. What is flash storage? Flash storage is any type of data repository or storage system that uses flash memory. Flash storage describes any device or system that uses flash memory. It's a broad term that can describe anything from a simple USB flash drive to a complex enterprise system that uses flash memory as part of the storage system. Flash storage is also relatively old technology, but started as a way to permanently store information without power being applied. Flash memory, both NOR and NAND types, was invented by Dr. Fujiro Mosoka while working for Toshiba circa in 1980. According to Toshiba, the name Flash was suggested by Mosoka's colleague Suji Arizumi because of the erasure process of the memory contents reminded him of the flash of a camera. Mosoka and colleagues presented the invention at the IEEE in 1984 International Electronics Devices meeting held in San Francisco. Intel Corporation saw the massive potential of the invention and introduced the first commercial NOR flash chip in 1988. So here are the different flash storage. We have here PCI flash card, SATA SSD, compact flash, micro SD cards, and of course the universal serial bus flash drive. So this is very familiar to everyone. This is also some examples of different flash storage. Also the different types or the different flash storage that is actually introduced in our industry. Flash storage introduced by Toshiba in 1984. Flash memory was developed from EEPROM or electrically erasable programmable read-only memory. There are two types of flash memory, NOR and NAND. The name refers to the type of logic gates used in memory cell. Logic gates are a fundamental building block of digital circuit. NAND-type flash memory may be written and read in blocks or pages, which are generally much smaller than the entire device. The NAND type is primarily used in memory cards, USB flash drives, solid-state drives, which are produced in 2009 or later, and similar products for general storage and transfer of data. NOR, on the other hand, is also a type of flash that allows a single machine word or byte to be written to an erased location or read independently. It is a type of non-volatile storage technology that does not require power to retain data. The two chips works differently. NOR flash is faster, but it's also more expensive and takes longer to erase and write new data. NOR is most often used in mobile phones. NAND, however, has a significantly higher storage capacity than NOR. It has found a market in devices to which large files are frequently uploaded and replaced. MP3 players, digital cameras, and USB drives use NAND flash. NAND devices are accessed serially using the same 8 pins to transmit control, addressing, and data. NOR flash memory supports 1-byte random access, which allows machine instructions to be retrieved and run directly from the chip, in the same way that a traditional computer will retrieve instructions directly from main memory. NOR flash has an SROM interface that includes enough address pins to map the entire chip, enabling the access to every byte stored within it. Some devices use both NAND and NOR. A pocket PC, for instance, may use embedded NOR to boot up the operating system and a removable NAND card for all its other memory or storage requirements. NAND or NOR flash memory is also often used to store configuration data in numerous digital products, a task previously made possible by EEPROM or battery-powered static RAM. The first NAND-based removable media format was Smart Media in 1995, and many others have followed, including multimedia card, secure digital, memory stick, and HD picture card. A new generation of memory card formats, including RSMMC, Mini SD, and Micro SD, and Intelligent Stick, features extremely small form factors. For example, the Micro SD card has an area just over 1.5 square centimeter with a thickness of less than 1 millimeter. Micro SD capacities range from 64 megabyte to 200 gigabyte as of March 2015. In consumer technology, mobile devices including phones, digital cameras, music players, and tablets also rely heavily on flash-based storage. These devices use flash chips instead of hard drive for storage. Now, how beneficial flash storage is. A move of spinning disks to flash chips brings benefits in 3 areas that are key to mobile devices. We have size, power consumption, and durability. It also tends to reduce heat and makes fans less necessary and cut down on device startup time. The biggest downside of the technology, however, is cost. A gigabyte of flash storage costs approximately 8 times as much as the same amount of space on an HDD, according to Forward Insight analyst Gregory Wong. Solid-state storage is a type of flash storage has helped to raise the wave of portable PC alternatives that has hit the market over the past few years, and in 2015 is likely to see the technology become more affordable and better performing. Because of its affordability and better performance, all the major tablets that have been announced and shipped this year use flash chips in place of a spinning hard disk drive for storage. All smartphones also use NAND flash, as do many netbooks. We have here advantages of flash storage. First, faster boot up times and file transfers, since all the data on an SSD can be accessed at once. And another one is the fact that SSD have no moving parts also makes them more durable, which means it is usually safer option to store sensitive data. SSDs also make little to no noise and require less energy to run and keep cool. Let's now first differentiate HDD and SDD physical appearance. Hard drives consist of various moving parts, making them susceptible to shock and damage, while SSDs use a non-mechanical design of NAND flash mounted on a circuit board and are shock resistant up to 1,500 grams per 0.5 millisecond. Speed is the #1 factor to consider when picking an SSD drive. So it's roughly going to be between 5 times to 10 times faster than HDD at reading data. SSD has an incredible system performance which unmatched speed. It is also the best option for operating system, applications, and working data. Also, read performance does not change based on where data is stored on an SSD. Generally low because the data can be read directly from any location. In applications where hard disks are the limiting factor, this results in faster boot and application launch times. And not sensitive to orientation, vibration, or shock. Usually do not expose circuitry. High-performance flash-based SSDs generally require half to a third of the power of HDDs. High-performance DRAM SSDs generally require as much power as HDDs and must be connected to power even when the rest of the system is shut down. They usually do not require any special cooling and can tolerate higher temperatures than HDDs. Solid-state drives, essentially semiconductor memory devices mounted on a circuit board, are small and light in weight. SSDs have no moving parts and therefore are basically silent, although electric noise from the circuits may occur.
Drawback of flash storage. Expensive as capacity gets bigger. Flash storage has capacity issues that prevent it from reaching the same size as higher-end hard disk drives. SSDs are uniquely sensitive to sudden power interruption, resulting in aborted writes or even cases of the complete loss of the drive according to wikipedia.org. How Flash changes the design of database storage engines. Over the past decade, SSD drives, popularly known as Flash, have radically changed computing at both the consumer level, where USB sticks have effectively replaced CDs for transporting files, and the server level, where it offers a price-performance ratio radically different from both RAM and disk drives. But databases have just started to catch up during the past few years. Most still depend on internal data structures and storage management fine-tuned for spinning disk. Key characteristics of Flash that influence databases. Random reads. Like main memory, but unlike traditional disks, Flash serves up data equally fast, no matter how much physical distance lies between the reads. However, one has to read a whole block at a time, so applications may still benefit from locality of reference because a read that is close to an earlier read may be satisfied by main memory or the cache. Throughput. Raw throughput of hundreds of thousands of reads or writes per second has been recorded. Many tools take advantage of this advantage to orders of magnitude better than disk, or more, and throughput continues to improve as density is improving according to Aerospike CTO Brian Bulkowski, because there are more blocks per chip at higher densities, leading to higher throughput. Latency. According to David Rosenthal, CEO of FoundationDB, read latency is usually around 50 to 100 microseconds, as pointed out by Slava Akhimeta, CEO of RethinkDB. Flash is at least 100 times faster than disk, which tend more towards 5 to 50 milliseconds per read. Like CPU speeds, however, Flash seems to have reached its limit in latency and is not improving. Parallelism. Flash drives offer multiple controllers, originally 9 and now usually more, or single higher performance controllers. This rewards database designs that can use multiple threads and cores and split up workloads into many independent reads or writes. The benefits of flash storage for database workloads. Flash storage technologies can immediately address the performance and input-output latency problems encountered by many database deployments. Who needs Flash? For the world of databases, there are three main reasons why you might want to switch to low latency Flash. Acceleration. Perhaps the most obvious reason is to go faster. There are many reasons why people desire better performance, but they generally boil down to one of two scenarios: not good enough now and not good enough for the future. In the former, bad performance is holding back an application, denying potential revenue or incurring penalties in some way. Either SLA-based financial penalties or simply the loss of customers due to poor service levels. In the latter, existing infrastructure is incapable of allowing increased agility and the ability to do more, offering new services, for example, or adding more concurrent users. Consolidation. Consolidation brings agility and risk benefits as well as the new and important benefit of cost savings. By consolidating and standardizing multiple databases onto a smaller pool of servers, organizations save money on hardware, on maintenance and administration, and on the holy grail of all cost savings, software licenses fees. If you think sounds like an exaggeration, take a look at this article on Wikibon, which demonstrates the Oracle license cost account for 82% of the total cost of a traditional database deployment. Consolidations allows for reduced CPU cores, which means a reduction in the number of licenses. But it also increases input-output as workloads are stacked, on the same infrastructure. The Wikibon articles argues that by moving to flash storage and consolidating, the total cost drops significantly by around 26%. In fact, virtualization, an increasingly prevalent option in the database world. The use of server virtualization technologies is allowing organizations to move to cloud in architectures, where environments are automatically provisioned, managed, and migrated across hardware. Virtualization brings massive agility benefits but also carries a risk because, just like with consolidations, input-output workloads accumulate on the same infrastructure. Unlike consolidation though, virtualizations add an extra layer of latency, making the input-output even more of a potential bottleneck. Flash systems now make this option practical. Databases love flash if they create lots of input-output. There is lots of random input-output, high amounts of parallelism, large input-output wait times. These are all great indicators, but the next two should be considered the golden rules. I/O wait times are high, and I/O forms a significant percentage of database time. Performance won't improve if there isn't any I/O, single-threaded workloads, application serialization points, CPU-bound systems. The building blocks for flash storage systems: solid-state drives or SSD, PCIe peripheral component interconnect express cards, PCIe as SSD. There are several ways to use these building blocks within the computer storage stack. The approach taken determines how the stack incorporates the hardware and how applications can benefit from flash performance. There are 4 distinct use cases. Flash as cache in the server. Usage example. This implementation is useful for mission-critical servers that experience occasional and unpredictable bursts in activity from multiple application sources such as OLTP or data analytics. Caveats. While this use case offers the fastest access to cached data, it does require server management. Flash as cache in the storage system. Usage example. This is a great way to increase read performance across all of the servers accessing a network storage system. Caveats. While this method offers automatic caching of all hot data in a storage system, it may quickly fill if not sized properly. Flash as disk in the server. Usage example. This can be useful when a dedicated server with direct attached storage needed for a high-performance application and network storage is not a major consideration. Caveats. Although this is often the easiest implementation of flash in SSDs, the inability to upgrade or reconfigure flash components without halting the server may present problems in some environments. Consider your options in 2 dimensions. As you can see, there are a number of options available when it comes to flash storage. So split the decision into 2. Decide on 2 form factor, PCIe card or SSD device, and then decide how best to implement flash for your application, either as a replacement for HDD or as an HDD cache accelerator. This is the end of this video. Thanks for watching.
So that's it. Thank you for listening, and we hope that you've learned something about flash storage today. Till next time, classmates and Ma'am Thelma. Again, this is Miss Marilou Benoza together with Mr. Erwin Benitez saying thank you and God bless.